Our next speaker, and also the last speaker for today, at least in this session. So I have the pleasure to introduce Mrs. Miriam Schuster from the Technical University in Darmstadt. So Miriam, she received her PhD last year, and she studied about viscoelastic properties of interlayer materials. And nowadays she has a postdoc position at the Technical University and is also managing the new Glass Competence Center of the Technical University. So I'm not sure if you are all aware about that there's a new Glass Competence Center in place at the university. I think it's a quite interesting development as a testing and research lab, so maybe Miriam can give you more information if you want, so don't hesitate to ask her. And so her topic today will be the quantification of the linear viscoelastic behavior of multi-layer interlayers. So please welcome Miriam, and Miriam, the stage is yours.
Yes, as you heard, we have the Glass Competence Center. Thank you for talking about that. If you need some more information, don't hesitate to ask me. So today, I want to talk about multilayer interlayers and how to quantify the linear viscoelastic behaviors of those. I want to start with an introduction and motivation, then talk about the mechanical behavior of multilayers, show you the experimental investigations that we did, show you the results and discussion, and finally I will close the presentation with a summary and outlook. So why do we use multilayers? So by using different layers or materials as interlayer layers, we can combine the different positive properties. And one example in laminated glass in the architectural context is acoustic barrier performance, as we see, for example, in this picture. In order to have a good acoustic performance, we need a high damping. And high damping is achieved with very soft interlayers. However, soft interlayers are more complicated to process, and hence stiffer layers are used and put around the softer cure layer in order to enhance the laminate processing. And in total, we have then a tree layer, which is shown in this scheme. So we have two skin layers and in the middle a cure layer. And now the big question is, can the material behavior of this tree layer be predicted from the material behavior of the individual layers? But first, let's have a look at the material behavior of polymers in general. As we all know, there is a time-dependent material behavior which can be described in the linear viscoelastic weight by a generalized Maxwell model and mathematically be described by a Prony series. Thermorheological simple materials also have the advantage that the temperature dependency which occurs in all the polymeric interlayers can be described with a shift factor, which means that when we change the temperature, the relaxation function is shifted along the time axis. And those temperature-dependent shift factors can also be described with some models, and one of the most common models is the WLF model, which is shown here. And now, in order to find the material parameters, which are then the Prony parameters and the time-temperature superposition principle, we need to do some tests. And the most common tests to identify those parameters are dynamic mechanical thermal analysis, short DMTA tests. The result of such tests are a bunch of curves. Here we see shear modulus, values in dependency on frequency, and each of the lines is one curve at a specific temperature. And with these curves, we can generate a master curve by shifting them purely horizontally, and this master curve is then valid for a certain reference temperature. And the shift factors that were needed to generate these master curves are depicted in the graph on the bottom. And now we can use the master curve and fit the Prony parameters to this curve, and we can use the shift factors and determine the parameters of our time-temperature superposition principle. When this is done, we need a validation, and therefore often 4-point bending tests on laminates are performed. Okay, now let's have a look at multi-layer interlayers. So we have here a glass with a multi-layer. In this case, it's a 3-layer. And when we bend this laminate, then we have shear in our multi-layer. And we see that the individual layers are connected in series. So when we want to transfer this to real-logical models, then we have the 3 generalized Maxwell models for the 3 layers connected in series. With the dark color, we see the skin layers, and the lighter color in the middle is the cure layer. So now we want to determine the relaxation function, or the material parameters for this 3-layer. And therefore, we are looking at a relaxation test. So we are applying a strain and keeping it constant. And what is of interest would be the response of the combination of those models, and this is called the effective modulus of the 3-layer. So as we see, this is a connection in series, which means that we can change the order of the connection of the individual layers. And when we have identical skin layers, we could move the 3rd generalized model, which was depicted in the slide before, just to the first one and combine them, and respecting a total thickness for the skin layer. So this makes it already easier for the calculation. In the next step, I try to do some parametric studies with simplified models, and to further simplify, I decided to firstly only consider 1 Maxwell model per layer, which then looked like this. So we have the skin layer and the cure layer, but with a reduced amount of parameters. And then the first thing I considered was equilibrium, which means we are looking at the stress, and we see that the stress in each of those layers is the same and consists of the sum of the stress in the elastic spring and the Maxwell element. Second thing is the kinematics. It's a relaxation test that means that the total strain remains constant, and hence the strain weight equals 0. And the total strain can be calculated from the strain of both interlayers. And next, I consider the constitutive models for the elastic springs and for the generalized Maxwell models. And by combining all those equations, we obtain a system of differential equations. I don't want to go into detail for that, but when looking at some initial conditions, which mean the conditions at the time equals 0, then we can solve this differential equation system, for example, analytically or numerically, and obtain the stress response for this multi-layer, and with the stress response and the applied strain, we can calculate the effective modulus for our multi-layer. At this point, I want to point out that even if the total strain is constant, the strain in the individual layers may change over time. And this means that the different layers influence each other, and this makes the solution of this differential equation system very long. So another method to come to the effective shear modulus value of a multi-layer is to consider creep instead of relaxation. And in a creep test, we have the stress which is held constant. However, we do only know our relaxation parameters for the individual layers, since the Prony parameters are relaxation parameters. But we also know that in the Laplace space, there is a simple relation between creep and relaxation, which is depicted here. So what did we do? We considered our relaxation functions for the individual layers, transferred them into the Laplace space, then used the relation between creep and relaxation, used the inverse Laplace transformation to get the creep function, and then were able to determine the creep strain for each of these layers. And then we could calculate the total creep strain. With the total creep strain and the applied stress, we can calculate the creep function, and again, using Laplace space, we can transfer this back to the relaxation function. So this seems also very complicated at first sight, but in fact, this is a really short code in MATLAB, and it is also really fast to calculate, even if we are considering more material parameters for the individual layers. However, besides those longer or more complicated combinations, we also considered a simplified rule of mixtures. In this model, the Maxwell elements of the individual layers were neglected, and only the springs, the elastic springs, were considered. And the stiffness of those elastic springs are in fact dependent on time. And we see that here the solution is very short, and of course we obtain a very quick prediction of the material behavior of the multilayer. So next I did a comparison of all those prediction formulas, and we see here in the black dotted line is layer 2, black dashed line is layer 1, so 2 layers with some randomly picked material parameters. And in green and blue, we see the solutions of the differential equation system. One time the analytical solution, one time a numerical solution, and we also see the solution using the Laplace transformation. And all those 3 lead to the exactly same response, which is here. And in red, we see the result from the simplified rule of mixture. And here we see that there is a deviation between the simplified and the exact solution. And this deviation is depicted in this graph in the lighter color. So we see we are around 30% of deviation in some time range. And here I've also varied the parameters. For example, in this example B, we have another combination of material parameters. And here again, we see that there is a deviation between the exact and the simplified solution. But when we are looking at, again, other combinations, for example, for D and E, we see that the deviation between the exact and simplified solution becomes a bit smaller. We do also see in the example E that when one of both layers is very soft, then the multilayer will also behave soft. So the influence of the softer interlayer is very high. Okay, let's come to the experimental investigations. So first, we did some DMTA tests. We did them on a trilayer from Koarei, Trosifol as the multilayer. And we also did the tests on the individual layers. And we investigated temperatures between -20 and +105 degrees Celsius. And the temperature steps were 5 degrees Celsius. For each of those tests, so the multilayer and the individual layers, we generated master curves. They are depicted here in the frequency range. So we have in continuous line the storage modulus, and in dashed lines the loss modulus curves. In all 3 cases, it was possible to create master curves by purely horizontal shifting. And what is interesting for the multilayer, we see here a double dip in the storage, but also in the loss modulus curve. Next, we had a look at the time-temperature superposition principle, or first at the shift factors, which are depicted here. The circles are for the multilayer, the square for the cure, and the triangle for the skin. when looking at the triangles for the skin, we see that there's a change in curvature, and therefore we decided to look at two different temperature ranges, one above 25 degrees Celsius and one below 25 degrees Celsius, and then we fitted the WLF function to those two temperature ranges, and we also see that in the lower temperature area we have negative constants, while in the higher temperature area we have positive constants. We also fitted a WLF for the cure layer, and for the multilayer we only fitted in the range of 25 degrees Celsius and upwards, since below the shift factors are exactly the same than for the cure interlayer. Okay, then when we completed the DMTA test, also creep tests were done. They have been done at the University of German Armed Forces and at Friedman and Kirchner at different temperature levels, so 20 degrees Celsius, 30 degrees Celsius, and 40 degrees Celsius. And here only the multilayer was tested, not the individual layers. So what was done? A load was applied for a certain time. The displacement was measured, and from the measured displacement, the shear modulus was back calculated using some meta models. And here we see the results. So again, or maybe first we have three graphs. The first one is at 20 degrees Celsius, then 30 and 40 degrees Celsius. We have the master curves, or the evaluated Prony series for the skin layer, the dotted line, the cure layer, which is the dashed line, and the master curve obtained from DMTA for the multilayer, which is the black continuous line. Then we see the symbols. We have the circles and the squares, which are the results from the creep tests. And we have the gray lines, which are the predictions. So two different predictions were used. The one using the Laplace transformation and the simplified rule of mixture prediction. And first of all, we see that the creep test and the DMTA results fit quite well for all the temperatures. However, when looking at our prediction, we see that also the prediction fits quite well to the creep test until we arrive at higher load durations. There we have a deviation, and we still don't really know where this deviation comes from. Mathematically spoken, it comes from here the decrease of the stiffness in the cure layer, but why we don't observe it in the bending test is not clear yet. So now let's come to the summary and outlook. So we looked at the rheological models of tree layers and were able to predict the material behavior of a multilayer from the material properties of the individual layers. We solved the differential equation system. We considered the creep behavior, and we looked at the simplified rule of mixture. And I think, at least for this tree layer, the simplified rule of mixture approximation is good enough to predict the material behavior. We did some DMTA tests on the individual layers and also on the tree layer. And we had a comparison with all the solutions, the DMTA and the bending creep tests. And to conclude, I would say it is possible to predict the behavior of multilayer interlayers when we know the properties of the individual layers. So that's it. Thank you for your attention. And if you have some questions, please don't hesitate.